Section 6.2 is volumes using cylindrical shells. This is similar to what we did in section 6.1 in that it's still going to be a solid of revolution. We're going to be finding the volume of a shape, a solid shape that we revolve around an axis. But it's going to be different in that the shape that we develop is not going to be a wheel or a donut shape. It's going to be a cylindrical shell. If we had a shaded region that looked like this, where we have this blue shaded region right here, and we had to revolve it around the line x equals -1. If I were going to use a washer method, because it is a hollow shape, I could not use the disk method, I would have to use a washer method. My outer radius would be this function right here. Correct? And my inner radius would be this function right here. The problem is we're given the function as y equals a function of x is just one function. And I would have a delta y, so I would have to solve this equation for x and use x as a function of y, not y as a function of x. This equation is extremely difficult to rewrite as x as a function of y. We need a different method to use to find the volume of this shaded region. Because we have y as a function of x, we would like to use a vertical rectangle, and that vertical rectangle, the width of it would then be a delta x. So then we could use the function as it's written, y equals 3x minus x squared. The problem is for the disk and the washer method, our representative rectangle here has to be perpendicular to the axis of revolution. This rectangle is parallel to the axis of revolution. So we're going to develop what's called the cylindrical shells or the shell method for volumes of revolution, and we use that when the rectangle is parallel to the axis of revolution. That's one difference between the disk or the washer method and the shell method, is the orientation of the representative rectangle to the axis of revolution. So if I take that shape and I revolve it around the line x equals -1, what I generate is a shape that looks like this, and it's a cylindrical shell. The thickness of that shell will be the thickness of this representative rectangle right here. And if I were to take that shell out, that's what I've done in this picture right here, and I take that one single shell out of this shaded region, and I cut that shell along this purple line right here, and I roll it out flat. What I have then is a slab that looks like a rectangular prism. And we know how to find the volume of a rectangular prism. It's the base times the height times the thickness. Well, the base of this shaded region would be this region right here, and that comes from this edge of the circle. How do I find the base of a circle? It's the circumference, right? So the base is going to be equal to the circumference, and the circumference of a circle is 2 pi r. 2 pi times the radius, where the radius is going to be this distance right here, which is the distance from the axis of revolution to the outside edge. That hasn't changed. And that shell was generated by revolving that rectangular region right here. So the distance from the axis of revolution to that rectangle would be our radius. The height of the shell is going to be the height of the rectangle. So this distance from the bottom of this shaded region to the top of the shaded region would be the height of the rectangle. So that's going to be the top minus the bottom function. And then the thickness for this problem is going to be the thickness of that rectangle, which is our delta x, which when we set up an integral turns into our dx. So to find the volume, we would look at 2 pi r times the height times the thickness. And when I set up an integral to find this volume, that 2 pi is a constant. I'm going to pull that out of my integral. And then how do we find the bounds of our integral? Well, it's going to be the bounds of the shaded region, which for this problem is going to go from here to here. So that's going to go from 0 to 3. And then our radius is the distance from that rectangle to that axis of revolution at x equals -1. Well, that distance is a horizontal distance, so we're looking at the right-hand function minus the left-hand function. So the right-hand function is the rectangle, and that's going to be x as it slides along from 0 to 3. So that's going to be x minus the left-hand function is -1. And then the height of that function is our function of y, where we said y was equal to 3x minus x squared. And then the delta x becomes our dx, which is our variable of integration. So notice in this problem, I only have x's and my variable of integration is x. So everything is set up correctly. Then we would clean this up and proceed to find the volume by integrating this integral. The question was, where did the x minus -1 come from? And that is our radius. where the radius is the distance from the axis of revolution to the outside edge. We're going to integrate over the bounds for the shaded region. Go back up and look at our original picture. The question was, how do we determine our bounds of integration? And the bounds of integration are always determined by what your shaded region is along the x-axis, because our thickness is a delta x. So our shaded region starts right here at x equals 0, and it stops right here at x equals 3. So our bounds of our integral are 0 to 3. The question was, when you're working a problem like this, they'll give you the shaded region. They'll give you enough information that you can figure out what the shaded region is. Will you be told if the rectangle is going to be a delta x or a delta y? And the answer is no. That's up to you to determine. For any time you use the shell method, your representative rectangle is going to be parallel to the axis of revolution. So if I tell you to solve a problem using the shell method, know that your rectangle will be parallel to the axis of revolution. If I said use the disc or washer method, then your rectangle would have had to have been perpendicular to this axis of revolution. But the washer method won't work here because I have the same function on the outside edge as I have on the inside edge. So does that make sense why the washer method wouldn't work and we had to come up with a different method? I understand the question better now. The question now is, how do you determine where to draw the rectangle? Should I draw the rectangle right here? Should I draw it right here? Should I draw it right here? And the answer is, it does not matter, because the bounds on this rectangle from 0 to 3 tell me that this rectangle is going to start out right here at 0, where it's just a point, and then that's going to slide along from 0 to 3. So that rectangle is going to change as I move along the bounds. Remember the limit definition of an integral that says we're taking all of these different rectangles and we're adding them up as they move from the lower bound to the upper bound. So this rectangle is going to be sliding along from 0 to 3, and I have no way of drawing with 2 points on the screen so you can see, but as it slides along, when we start out at x equals 0, my rectangle is very, very small. When I'm at x equals 1, this would be my rectangle, and then as I move along to x equals 2, this would be my rectangle. The rectangle is sliding along through the bounds. So if you can envision a whole bunch of different rectangles, or one rectangle just changing shape as you move along from 0 to 3, that's what's happening. So whenever I draw at the shaded region to set up the problem, and then I put in a representative rectangle, it doesn't matter where that representative rectangle goes. I'm just drawing one static picture so that I can envision what's going to be sliding left to right or bottom to top. So the question was, can we just put our rectangle at a nice easy number as it moves, anywhere in the shaded region? And the answer is yes. And it doesn't even have to be on a number. I just wanted to use that rectangle to determine what is the thickness going to be, and then how do I determine what my radius is. I'm not going to finish this problem. I've got some other problems that we're going to look at for examples. I just wanted to use this example to explain how, when you revolve a rectangle around a fixed line and you're using the shell method, it creates a three-dimensional shape that ends up being a rectangular slab, where the base of that slab is going to actually be the circumference of the circle. The height of that slab is going to be the height of your rectangle, and then the radius is the distance from the axis of revolution to the edge of that shell or that rectangle. Yeah, and I did say that the radius is the distance from the axis of revolution to the shell, not to the inside edge of the shaded region or the outside edge of the shaded region. It's the distance from the axis of revolution to the rectangle as it moves from 0 to 3 for this problem. Once you get the geometry of this problem down, these problems become easier. I remember when I was a student, the shell method for me was more difficult because it's the method that I learned second. But when you have a problem similar to this, it's the only method that's going to work. Now, there are some problems that you could use either method, the shell method or the washer method or the disc method, and it's up to you to decide what's the best method to use. And on your test, I'm going to have questions where I ask you to sketch the shaded region and then set up either the disc or washer method, depending on if it's a solid shape or a hollow shape, and then also set up an integral for the shell method. Your variable of integration will change between the disc and washer method and the shell method, because your rectangle goes from either being vertical or horizontal, so that you change the dy or the dx. And we'll see some examples of that as we go along. So when the region shown in this picture is revolved around a vertical line, x equals L, here's the vertical line, x equals L, a solid is produced which can be sliced into cylindrical shells. So we have a whole bunch of these cylindrical shells that we're going to be adding the volumes up as we go. And that's how we developed this formula for the shell method. We said the volume is 2 pi times the radius. Remember, this was from the circumference of the circle, and then times the height, so that's the base of our rectangle times the height times the thickness. Well, that's our shell that when we cut it and lay it flat, it ends up being a three-dimensional slab that looks something like this. And forgive me, but they don't make calculus teachers take art or engineering graphics. So the thickness of that would be my delta x. This would be the height of the rectangle. And then the distance from here to here would be the circumference, which is 2 pi times the radius. So let's look at an example problem. In example 1, we're told to use the shell method to find the volume generated by revolving the shaded region about the y-axis. So we're going to be revolving this region about the y-axis. I have already drawn in our representative rectangle. Notice this red line right here is parallel to the axis of revolution. That means that our thickness is going to be a delta x. The radius that we need then for this rectangle is going to be the distance from the axis of revolution to that rectangle as that rectangle slides along from 0 to 2, because the bounds on our integral are going to go from 0 to 2. So to find the volume using the shell method, we're going to do 2 pi times the integral from 0 to 2, because that's where the shaded region is along the x-axis. That's going to be our bounds on our integral. So it's 2 pi times the radius times the height of the rectangle, and then my variable of integration will be dx because the thickness of the rectangle was delta x. As this rectangle moves from 0 to 2, what is my radius going to be? It's going to be x, right? As x moves from 0 to 2. So I've got the volume is going to be 2 pi times the integral from 0 to 2 of x times, and then the height of the rectangle is going to be this function right here. So as that rectangle slides along from 0 to 2, the height is going to change according to this function, 2 plus, I'm going to say 1/3 x squared dx. In order to evaluate this integral, I need to distribute this x across here, and then that's going to give me that the volume is equal to 2 pi times the integral from 0 to 2 of 2x plus 1/3 x cubed dx. And now when we integrate this, our constant stays on the outside, and when I integrate 2x, what do I get? I add 1 to the exponent and divide by the new exponent. Well, the new exponent is 2, and 2 divided by 2 is 1. So I'm just going to leave that as x squared. And then when I integrate 1/3 x cubed, I'm going to add 1 to the exponent and then divide that by 4. And 1/3 times 1/4 is 1/12. And then our bounds on our integral will go from 0 to 2. And now it's just a matter of doing the arithmetic. So we plug in our upper bound of 2, and that's going to give us 2 squared plus 1/12 times 2 to the 4th minus, and then plug in your lower bound, you get 0 squared plus 1/12 times 0 to the 4th. And then we take care of the arithmetic, and that's going to give us 2 pi times 4 plus 2 to the 4th is 16 divided by 12 is 4/3 minus, and both of these terms are going to go to 0, so that's going to give us 32 pi over 3. Does it make sense where every part of the integral came from? The challenge on these is going to be setting up the integral. The question was, is dx our delta x? Yes, the dx comes from the thickness, which is delta x. If when I set up the rectangle, it was a horizontal rectangle, the thickness would be delta y, so then I would use dy for my variable of integration. Example 2. Now we want to use the shell method to find the volume generated by revolving the region bounded by the line y equals 1.9x, y equals negative 1.2x, and x equals 4 about the x-axis. So I've already graphed this region for you, but on your homework and on your exam, you may not see the graph. You may have to draw the graph. This first line here with the positive slope would be the line y equals 1.9x. The line with the negative slope would be y equals negative 1.2x. And then this vertical line here is x equals 4. And so the shaded region is the region that's bounded or trapped by all three of these equations. So that's the grayed out region I have here. I want to revolve this about the y-axis. And that means that my representative rectangle then is going to be parallel to the axis of revolution, and my thickness of that rectangle is a delta x. So what will be my variable of integration? X will be my variable of integration. I'll use a dx on my integral. Could I have solved this problem using the washer method? It is possible, but I would have to set up two integrals. So let's go into a little bit of a hypothetical here. If I wanted to use the washer method, my rectangle would have to be perpendicular to the axis of revolution. So here's a perpendicular rectangle right here, and the right-hand function would be x equals 4. The left-hand function, I would solve this equation for x, and then I would get x as a function of y, and the thickness would be a delta y. When I go above the line x equals 0, the function on the left-hand side changes. So here I would have for the right-hand side x equals 4, but for the left-hand side I would have this function y equals 1.9x. So because I've changed functions, I could not just integrate it from this point to this point along the y-axis. I would have to set up two integrals and do the first integral from this point right here to 0, and then from 0 to this point right here using two different functions for the left-hand side. So that's why I would rather just solve the problem setting up one integral, and the only way to do that is to use a vertical representative rectangle so that the top hand function and the bottom hand function stay the same all the way from 0 to 4. So that's why the shell method is the better method to use here. I'm trying to help you decide when to use which method. So if you can solve a problem by using only one integral, that's probably the one you want to go with. Plus, when you're given y as a function of x here, you probably want to use a delta x so you don't have to solve for x as a function of y and change your variables. So to find the volume of this, we know it's going to be 2 pi times the radius, and the radius, remember, is the distance from the axis of revolution to this rectangle. As x moves from where to where, what are our bounds on this problem going to be? From 0 to 4, those are the bounds along the x-axis of the shaded region. As this rectangle starts out at 0 and it moves along to 4, it would be getting taller as we move closer to 4. But as that rectangle moves along from 0 to 4, the radius is going to change from 0 to 4 as well, isn't it? So that means that my radius is just going to be x. And then the height of this rectangle will be the top function minus the bottom function. The height is going to be the top function minus the bottom function. And the top function is 1.9x minus, and then the bottom function is negative 1.2x. And 1.9 minus negative 1.2 is 1.9 plus 1.2, and that's going to be 3.1x dx. So there's 2 pi times the radius times the height. And now we want to multiply by x, and that's going to give us 2 pi times the integral from 0 to 4 of 3.1x squared dx. And when we integrate this, we're going to add 1 to the exponent, which makes this x cubed, and then we take 3.1 divided by 3, and we evaluate this from 0 to 4. So that's going to be, let's see, 3.1 divided by 3 times 2 ends up being 31 pi over 15, I believe, times x to the third from 0 to 4. And when we plug in our upper bound, that's going to give us 4 cubed, which is 64, minus 0 cubed, which is 0. And so 31 times 64 is 1984 pi over 15. And that would be our final answer. Evaluating the integral is not as difficult as setting up the integral. That's going to be the challenge. The question was, is the radius pretty much always going to be x? And the answer is yes, if you're revolving around the y-axis. But notice up here in this example, the radius was not just x. It was x minus a negative 1. Because I revolved around the line, x equals negative 1 right here. So the way you determine the radius, notice that distance is a horizontal line. So it's going to be the right-hand function, which is x, minus the left-hand function, which is negative 1, and x minus a negative 1 ended up being x plus 1. In example 3, we're told to use the shell method to find the volume generated by revolving the region bounded by x equals 2 square roots of y, and that's this function right here. It's the parabolic shape, x equals 2 square roots of y. X equals negative 0.4y, And so that's this line right here, the green line, x equals negative 0.4y, and y equals 10. So this is the line right here, y equals 10. We want to revolve this now about the x-axis. So when I revolve this about the x-axis, my representative rectangle has to be parallel to the axis of revolution, which means that this is now the thickness is going to be delta y. So my variable of integration is going to be y. I need x as a function of y. So let's set up our integral. So we have volume. The volume is equal to 2 pi times the integral from where to where? Do I look for my bounds on my shaded region along the x-axis or along the y-axis? The y-axis. So that's going to go from 0 to 10 and then times the radius. The radius is this distance from the axis of revolution to this rectangle. So the radius is going to be y, which is where the rectangle is as it moves from 0 to 10, minus 0, top minus bottom, which is just y. So this is going to be 2 pi times the radius times the height. The height, when you turn it on its side, is going to be length. So that's going to be the right-hand function, which is 2 square roots of y, minus the left-hand function, which is negative 0.4y, and then the thickness is delta y, so we're going to use a dy in our integral. So this is your radius, and this is the height or the length, and it's found by taking the right-hand function minus the left-hand function. Anytime you have a horizontal line, remember it's right minus left. If you have a vertical line, it's top minus bottom. Then we need to clean this up. So what we're going to do is we're going to distribute this y across here as well as that negative and rewrite our integral. So this 2 square roots of y I could write as y to the 1/2 power times y to the first, which is 2 halves, multiplying with the common base, add the exponents. So that's going to give us 2y to the 3/2 power. And then minus a negative is going to be plus 0.4y squared dy. So now we integrate. This is going to give us 2 pi times, when you add 1 to this exponent, there's already a 2 here. We add 1 to the exponent, that's going to give us y to the 5/2. Divide by 5/2 is the same thing as multiplying by 2/5. Plus 4/10 is 2/5. I'm just changing that decimal to a fraction because fractions are easier for me to think about. Add 1 to the exponent, and that gives us a y cubed. Divide by that exponent. It's the same thing as multiplying by 1/3. And then we're going to evaluate this from 0 to 10. So I just want to clean up the arithmetic a little since I'm doing this in my head. So that's going to be 4/5. Y, that's 2.5. So that's the same thing as looking at y squared times the square root of y, is it not? Y to the 5/2, that's 2.5, so that's 2, and then there's my 0.5 is the square root, plus 2/15 y cubed from 0 to 10. So when we plug in our upper bound, that's going to give us 4/5 times 10 squared times the square root of 10 plus 2/15 times 10 cubed minus, and then when you plug in a 0, I know we're going to get 0, but for the sake of the video, I'm going to show the steps. That's 0 squared square root of 0 plus 2/15 times 0 cubed. And then it's just a matter of cleaning up the arithmetic. 80 square roots of 10, and I can't simplify the square root of 10. Plus, that's going to be 1,000. Yeah, so this is going to end up being 400. And then we need to distribute that 2 pi across, and that's going to give us 160 pi square roots of 10 plus, oops, that's not 400, that's 400 over 3. So that would be 800 pi over 3. And this would be our final answer. And this is the exact form, not a decimal approximation. This would be the answer that I would want on a test. The question was, would it be technically wrong to get a common denominator here and just write this as one rational expression? The answer is no, it wouldn't be wrong, but it's not necessary. I would accept this as an answer, and I believe even in the back of the book, when you check your answers, it'll show these two terms. Here's the thing about Cal 2. There are multiple ways to represent the same correct answer. So as long as, let's say you're doing your homework and you want to check your answers, as long as the answer that you got can be algebraically manipulated into the answer they have in the back of the book, know that I would accept it on a test, which makes grading Cal 2 exams so much fun. So in summary, for the shell method, regardless of the position of the axis of revolution, either horizontal or vertical, the steps for implementing the shell method are as follows. First of all, very important, draw the region and sketch the line segment. They're using a line segment. I use a representative rectangle so I can see the thickness that is parallel to the axis of revolution. Shell and parallel rhyme. That's how you can remember the rectangle has to be parallel to the axis of revolution. Label the segment's height and length. That would be the shell height. And then the distance from the axis of revolution. That would be the radius. Then find your bounds on your integral. That's determined from the shaded region. It'll be the shaded region along either the x-axis if the thickness of your representative rectangle is a delta x, or the y-axis if the thickness of your representative rectangle is a dy. In this example, we're going to be using the same shaded region for all 4 problems, but we're going to change how we revolve this. So compute the volume of the solid generated by revolving the triangular region bounded by the lines 2y equals x plus 4, y equals x. So here's the line y equals x. This is the line 2y equals x plus 4, and x equals 0, which is the y-axis. So that means that our shaded region is going to be this region right here for all of these problems, because that's the region that's trapped between all 3 of those equations. Now we also need to know how to write this equation as a function of x and as a function of y. If I were to divide this equation by 2 on both sides, I would have the equation y equals 1/2 x plus 2, or if I solve this equation for x, I would have x equals 2y minus 4. I need both of those in case I'm working with a dy or a dx. I'm going to use the top function if I have a delta x, and I use the bottom function if I have a delta y. So I'm just going to go ahead and solve for those and get them now. In part A, we're asked to revolve this shaded region right here about the x-axis, and we're told to use the washer method. So when we revolve this around the x-axis, we generate a hollow shape, and we're told to use the washer method, which means that our representative rectangle has to be perpendicular to the axis of revolution. So there's 2 radii involved. We have an outer radius and an inner radius. The outer radius is going to be the top function, which we said is going to be, and this is a delta x. So I'm going to want to use the function y equals 1/2 x plus 2. The inner radius is that bottom function, y equals x. So for the washer method, when you set up your integral, the pi times the integral of the outer radius squared minus the inner radius squared. For this problem, that's going to give us the volume is equal to pi times the outer radius we said was 1/2 x plus 2 squared minus the inner radius is just x squared dx. And before you can integrate this, you've got to FOIL this out and combine like terms. And what are going to be the bounds on this shaded region? How do I get that point of intersection right here? I have the function y equals x and the function y equals 1/2 x plus 2. What would I do to determine what this point is? Well, it happens to be the point 4, 4. But what you would do is you would set those 2 equations equal to each other and solve for x. And when x is 4, y is 4. So what will be the bounds on this integral? 0 to 4. And then when I FOIL this out, that's going to give me 1/4. I tell you what, let's do scratch work over here. I have 1/2 x plus 2 times 1/2 x plus 2. So that's going to give us 1/4 x squared. And then when I multiplied the inside terms together, that's going to give me x plus another x, so that's plus 2x. And then when I multiply the last terms together, I get 4. That's what I get for this first term, minus x squared. So 1/4 x squared minus x squared gives me a negative 3/4 x squared plus 2x plus 4 dx. And I'm not going to take the time to evaluate this integral. You guys can do that. We've got 4 of these and we have more material to cover today. So I'm just going to set the integrals up for you. Are y'all okay with that? All right, for part B, we're asked to revolve this around the y-axis and we're told to use the shell method. So for part B, we're going to revolve this around the y-axis and we're told to use the shell method. Our shaded region is still this region right here. And my representative rectangle now has to be parallel to the axis of revolution. The thickness is still going to be a delta x. And remember, for the shell method, the volume is equal to 2 pi times the integral times your radius times the height. and this is a delta x, so we're going to use a dx here. Our bounds are going to go along the x-axis, so that's still going to be from 0 to 4. The question now is, what is my radius going to be? Well, the radius is the distance from the axis of revolution to that rectangle as x moves from 0 to 4. So for this problem, our radius is just going to be x. Remember, I told you, anytime you revolve around the y-axis, your radius is just going to be x. You only really have to worry about it if you're revolving around another line. And then how do I get the height of this rectangle? It's going to be the top function minus the bottom function. And just so you remember, our top function here is y equals x. And, well, actually, it's going to be our bottom function. And then this function is going to, the top function is going to be y equals 1/2 x plus 2. So to set up my integral for the volume, I get 2 pi times the integral from 0 to 4 of the radius, which is just x, times the height, which is going to be the top function, 1/2 x plus 2, minus x, the bottom function. And when I clean that up, that's going to give me 2 pi times the integral from 0 to 4 of x times 1/2 x minus x gives me minus 1/2 x, so that's going to be 2 minus 1/2 x. And then I would distribute this x across here, and that means to find the volume, I would want to find 2 pi times the integral from 0 to 4 of 2x minus 1/2 x squared dx. And like I said, I don't want to take the time to do this today. We have other things we have to do. Setting up the integral is typically the most challenging part. For part C, we're asked to revolve this around the line x equals 4 using the shell method. So when we revolve this around the line x equals 4, we're revolving around this line right here. And remember, this is the point 4, 4 on the graph. And because I'm using the shell method, my representative rectangle has to be parallel to the axis of revolution, which means that the thickness is a delta x. So when I set up my integral, I need to know two things. I need to know the radius and I need to know the height. To get the radius is the distance from the axis of revolution to that rectangle. That's my radius. And we said we take the right-hand function, which is 4, minus the left-hand function, which is the rectangle, which is going to be x as it moves along your bounds from 0 to 4. So that's what I'm going to use for my radius. So it's the distance from the right-hand function, which is the axis of revolution, to the left-hand function, which is the rectangle, and I just use the x for that. The other thing I need is the height, and the height is found by looking at the top function minus the bottom function. So when we look at the height, the top function is going to be this function right here, which we said was y equals 1/2 x plus 2, minus the bottom function is this function right here, that's just y equals x, and so the height is going to be 2 minus 1/2 x. So the volume is going to be 2 pi times the integral from 0 to 4 of, now my radius is 4 minus x, and I already explained it when we were talking about the picture, how we got the radius, times the height, which we said is 2 minus 1/2 x dx. Before I'm ready to integrate, what do I need to do here? You need to FOIL that out and simplify your integrand. So when I multiply my first terms together, I'm going to get 8. When I multiply my outside terms together, I get minus 2x. Inside gives me a minus 2x, so that would be a minus 4x. And then when I multiply my last terms together, I get 1/2 x squared dx. And so I would evaluate this integral using these bounds in order to get the volume. For part D, we're asked to revolve this around the line y equals 8 and use the washer method. So here's the line y equals 8. This is the line y equals x. And this is the line y equals 1/2 x minus 2, not minus 2, plus 2. For the washer method, our representative rectangle has to be perpendicular to the axis of revolution, which tells us that our thickness is a delta x. So we are going to be using x as our variable of integration. We determine the bounds by looking at the area along the x-axis, the shaded area along the x-axis. And remember, for the washer method, we use pi times the integral from 0 to 4 of our outer radius squared. And the outer radius here is the distance from the axis of revolution to this function right there. That's our outer radius. That function is y equals x. To get the length of the outer radius, we take the top hand function Let's do it this way. The outer radius is going to be the top hand function minus the bottom function. And for the outer radius, the top function is y equals 8, and the bottom function is y equals x. To get the inner radius, we look at the distance from the axis of revolution to the inside of our shaded region. And so, once again, we're going to be looking at the top hand function minus the bottom hand function. And the top function is still going to be 8, and the bottom function is going to be 1/2 x plus 2. When we distribute the negative and combine like terms, we're going to get negative 1/2 x plus 6. So I'm just going to write 6 minus 1/2 x. 8 minus 2 is 6 minus 1/2 x. And so for the washer method, when we set up our integral, we use the outer radius squared minus the inner radius squared dx. And so we would have to do FOIL or perform FOIL on both of these and then distribute the negative in order to get like terms and simplify the integrand so that we can integrate this. Yeah, I'll go ahead and set it up for this problem, but we're not going to actually integrate it. So that's going to give us pi times the integral from 0 to 4 of, when I square 8 minus x, we square the first term, double the product, and then square the last term, minus, and then do the same thing. Square the first term, double the product, and then square the last term. And then what we need to do is distribute this negative and combine like terms. So we get that the volume is going to be pi times the integral from 0 to 4 of 64 minus 36 is 28. And then we have a negative 16x plus 6x gives us a negative 10x. And then plus x squared minus 1/4 x is going to be plus 3/4 x squared dx. And so to find the volume, I would want to evaluate this definite integral. So let's just do a quick recap here. We've learned 3 different techniques for finding volumes of solids of revolution: the disk method, the washer method, and the shell method. For all 3 of these methods, we start by sketching a graph of the shaded region, and it's going to be the region bounded between some curves. Then we're going to look at a rectangle. We're going to sketch a representative rectangle. For both the disk and the washer method, that rectangle is going to be perpendicular to the axis of revolution, and then for the shell method, it's going to be parallel to the axis of revolution. As far as the shape of the shaded region goes, in order to use the disk method, we have to have a solid shape, meaning that our shaded region touches the axis of revolution everywhere. For the washer method, it could be part solid and part hollow, but there has to be a hollow somewhere. And for the shell method, it could be either a solid or a hollow shape. And then when I look at my integral, for the shell method, and I'm just going to use I'm going to leave the variable of integration off. It could be either a dy or a dx depending on the rectangle. Our integral here is going to be pi times the radius squared. And then you need your differential, d something. For the washer method, you're going to have pi times the integral of your outer radius squared minus the inner radius squared. And then it's either going to be a dy or a dx depending on the orientation of your representative rectangle. And then for the shell method, we have 2 pi times the radius times the height. And then we're going to have either a dy or a dx depending on the rectangle. The radius is always going to be the distance from the axis of revolution to the edge of something, either the outside edge of the shaded region, the inside edge of the shaded region, or the shell if you're looking at the shell method. So for the radius, it's always going to be the distance from the axis of revolution to the edge of something. It's either going to be the outside edge if you're looking for your outer radius, or the inside edge, or it's going to be the distance from the axis of revolution to that rectangle for the shell method. How we find those distances, it's either going to be, if you have a vertical distance, that'll be the top minus the bottom. If you have a horizontal distance, it's going to be right minus left, because you want a positive value. Larger numbers to the right, smaller numbers to the left. If you're looking along the x-axis, larger numbers are at the top, smaller numbers at the bottom. So you want to do a big number minus a little number so that these values stay positive. The question was, if we're doing the disk method and we have a solid of revolution, would it be possible to also use the shell method? And the answer is yes. And as you practice your homework problems, you'll get more comfortable seeing which methods you should be using. The only way to get good at this, guys, is to practice. There's no way around it. You've got to do the homework. And the more you do, the easier it gets. The easier it gets, by the time test comes around, the more comfortable you'll be during the test, the better your scores will be. So the secret to doing well on the test, unfortunately, is doing a lot of homework. Hours and hours and hours of homework. When I was a student, I did Cal 2 homework 2 to 4 hours a day, 6 days a week, just because I wanted to do well in the course. So if you want it, you can get it, but you've got to work for it. There's no shortcuts to this. You're going to have to work for it, the grade that you earn. And this wraps up section 6.2.